Hey guys, welcome to our next stepping stone in our adventure in A-level maths. This time we are looking at proof by exhaustion, which hopefully isn't going to leave us feeling like this. Although they can be quite time consuming and lengthy. So one thing I haven't said yet in the proofs playlist is that not every type of proof is appropriate for every different type of situation and thing that we want to prove, which is why we have all these different methods. Mathematicians are clever. If they've got a problem that they can't yet solve using maths that exists, sometimes they create a brand new branch of maths. So there are lots of different types of proof. We're going to see a few of them. In this one, we are looking at proof by exhaustion. So when we are proving something by exhaustion, we are basically working through every single possibility and proving our statement true. So I think the best way to explain this really is by example. So first of all, we're going to run through a non-mathematical example that will hopefully make the concept make sense, and then we'll get the maths involved. Okay, so here then, the statement that we want to prove true is that in English, no weekdays contain the letter G. So we want to prove this by exhaustion. So first of all, how many days in the week are there? There are 7. So we need to test all 7 days to see whether or not any of them contain a G in their name. So first up, we have not got our pen out. Okay, secondly, now that we've got our pen, the first day of the week is Monday. Now there's no G in Monday, so Monday works. Then we got Tuesday. Then we got Wednesday. Remember how I said this can be quite lengthy and time consuming? Yeah. So we got Wednesday. We got Thursday. We got Friday. We've got Saturday. And then of course we've got good old Sunday. So what we've done, we've taken this statement, so in English, no weekday contains the letter G, and what we've done, we've written out the name of every weekday. We can clearly see none of them contain a G, so we've exhausted every possibility. So we've proven that no weekday contains the letter G. Now, at the end of a proof, let's just say this implies then no G's. So at the end of a proof, you can either put a little end of proof sign like that, or my personal favourite, we can put a cheeky QED. Quite enough, done. So that's a non-mathematical example, a very obvious one, but hopefully that's explained the concept a little bit before we get the maths involved. So now we're going to start with a very simple mathematical example. Okay then, so our first mathematical proof by exhaustion, we want to prove that 11 is a prime number. So first up, remember the definition of a prime number. It means this number has no other factors than 1 and itself. So to prove this using exhaustion, we need to show that 11 has no other factors. Now, any potential factor has to be smaller than 11 and an integer. So the numbers that we need to test are 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now you might be thinking, crikey, do we really need to test all of those numbers? And luckily the answer is no. So imagine if we were doing this, as we will do, with a bigger number, there's going to be so many more elements that we need to test. Luckily, there are ways around having to test every single element. So, let's start off then with 2. Is 2 a factor of 11? So, if 2 is a factor of 11, it means if we divide 11 by 2, we get a whole number, which would also be a factor of 11. So, what happens if we do 11 divided by 2? Well, we're going to get 5.5. So 5.5 isn't a whole number, therefore, so we can get this notation going, therefore 2 is not a factor. So, we can cross 2 off of our list. What we can also do is think about the implications that this has. If 2 is not a factor, so if 2 is not a factor, well, what does it mean? This actually means there are no even factors. So, by 2 not being a factor, we can actually cross more elements off of our list. So, 4 can go bye-bye, 6 can go bye-bye, 8 can go bye-bye, and 10 can also go bye-bye. So, next we would want to test 3. So if we do 11 divided by 3, well, we're going to get 3.6 recurring, so it's going to be 3.66666 forever and ever and ever. So, we now know 3 is not a factor of 11. Now that also tells us any multiple of 3 cannot be a factor of 11. Now 6 has already gone because it's even, but we can now cross out 9 as well. So the next card we need to try is 5. So if we try 11 divided by 5, we get 2.2. So this tells us that 5 is not a factor. Now I forgot to write that up here for 3. This told us 3 isn't a factor. So we've just shown that 5 is not a factor, so we can cross him out. That leaves us with one more possibility, which is 7. So if we try to do 11 divided by 7, we will get 1 point some stuff after the decimal. So 7 is also not a factor. So, what we've done, we've now crossed off every possibility in our list of potential factors. None of them are a factor. So, end of proof. Quite enough done. QED 11 is prime, as we already knew. So, it does get trickier. As I said, that's a simple example to start us off. Again, what we've done there, to prove 11 is a prime, we've exhausted all the potential factors less than 11. We've shown none of them are a factor. Jobs are given. Okay, second example. So here we want to prove that 79 is a prime number. So 79 is quite a bit bigger than 11 relatively. Do we want to list all the possible factors of 79? No, we don't. With 11, it was still practical, it was doable. With 79 though, there's 77 numbers that we would have to write down. We don't want to do that. So, we're going to start off in much the same way that we started with 11 though. Let's try 79 divided by 2. So let's see if 2 is a factor. So 79 divided by 2 is 39.5. So 2 is not a factor. What does this mean? This means then there are no even factors. If you're wondering why that's true, think about it. For example, if 4 was a factor, then 2 would have to be a factor because 2 goes into 4. So we know there are no even factors. That's good. That already rules out half the possibilities. So that's quite a nice chunk of work done already. Next, let's see what happens if we divide 79 by 3. So 79 divided by 3 then is going to be 26.3 recurring. Now this tells us then 3 is not a factor. Now let's think about the implications of that. If 3 is not a factor, then 6 cannot be a factor. 9 cannot be a factor. Again, if 9 was a factor, 3 would have to be a factor because 3 goes into 9. So, we now know then, no multiples of 3 can be a factor. So again, that's ruled out quite a nice chunk. And the next thing we have to go to then is 5. So let's test 5. 79 divided by 5. Well, that's going to give us 15.8. So, what does that tell us? That tells us 5 is not a factor. Thus, no multiples of 5. So thus, no multiples of 5 can be a factor. So the next thing to try would be 7. So let's have a go with 7. So if we do 79 divided by 7, we get 11.3 if we go to 1 decimal place. So, you guessed it, 7 is not a factor. So, what are the implications of that then? Well, if 7 isn't a factor, that tells us no multiples of 7 can be a factor. Now, let's stop there for a moment and see what we've done. So we first of all, we tested to see if 2 was a factor. Then we tested to see if 3 was a factor. Then 5. Then 7. What numbers here are we testing? We're testing the prime numbers. So as we cancel out multiples of these potential factors as we go, what's happening is we are now just testing the prime numbers. When we've tested 2 and shown that it's not a factor, we then know every multiple of 2 is not a factor. Same for 3, same for 5, same for 7. So what we're now doing, we are just testing the prime numbers. So the numbers that those smaller prime numbers go into. Now we get to this point and we think to ourselves, oh, do we then need to try every prime number less than 79? Luckily, the answer is no. So this requires a tiny little bit of cheeky mathematical thinking, which I'm going to take you through now. Okay, so first up, a cheeky little side note. So, I hope that you all agree with me that 6 times 6 is equal to 36. Yeah? So, we could say the square root of 36 positively is 6. Well, another factor pair of 36. We could say 4 times 9 is equal to 36. That's also true. Now, let's think here about what's happened. So, 4 is less than 6, and 6 is less than 9. So, this factor pair of 36 uses one factor that is less than the square root of 36 and one factor that is greater than the square root of 36. So what happens with these factor multiplications is exactly this for any number. If you're not dealing with the square roots of the number, then one factor is going to be less than it, one factor is going to be more than it. So we're now going to use this idea to help us sort out 79. So, if we go back here, let's do our proof all on one page. Let's think about the square numbers that are either side of 79. So, what's the square number smaller than 79? Well, it's 64. So we know 64 is less than 79. We know 79 is less than 81. Now, if we square root all three parts of our inequality here, we get 8 is less than root 79, which is less than 9. So, what's this telling us? Well, we know 79 is not a square number. We know that root 79 is somewhere between then 8 and 9. So root 79 is 8 point something. So, well, what do we know here then? We know root 79 times root 79 would give us 79, but we've ruled out every number less than or equal to 8 as a factor of 79. So what we can say now is that, well, we know there are no factors of 79 that are less than or equal to 8, except 1. So if there are no factors less than or equal to 8, then that tells us there can be no factors greater than or equal to 9, except 79. Okay, if there was a factor less than or equal to 8 other than 1, then to balance that out, there would have to be a factor greater than or equal to 9, but there isn't one less than or equal to 8, so there are no factors greater than or equal to 9, so we've actually proven it. Therefore, 79 is prime. So, we've proven it. We can make a cheeky little QED. Let's put a smiley face here. Why not? Okay, so hopefully you followed that proof. Things are getting a little bit trickier. I'm going to leave it here for this video. Next video is going to be some more examples of proof by exhaustion. I think we'll do an even bigger prime number, and we can do other types of proof. It's not just to do with primes. So if you have any questions up to here, guys, be sure to put them down below in the comment section. Hope you've enjoyed it. Take care.